Um, so today we have a guest speaker, Nathan Lambert. Nathan, I overlapped with Nathan when he was starting at Berkeley, and it's great to see that he's kind of gone on and done quite a lot of exciting work. We also kind of briefly overlapped actually at Facebook AI Research, where Nathan was interning that summer when I was also kind of visiting researcher there. Nathan, it's great to see you. Are you still in Berkeley right now, or?
Yeah, I'm in Berkeley.
Okay, yeah. How's the weather up there?
I mean, it's great.
Always, yeah. Yeah, it's been a while, but I should travel to Berkeley again. Great, yeah. So thanks again, Nathan, for taking the time, and yeah, excited to hear about what you have to say today.
Yeah, thanks for the intro. I definitely am happy to take questions throughout, and especially clarifying questions if you want to discuss anything. I think I'm more likely to be short on time than go too long, so it can be time for discussions. And yeah, so kind of what I'm going to talk about today is planning through exploration and exploitation in model-based reinforcement learning, and generally trying to figure out what these mean, what exploration and exploitation look like in these classes of algorithms. So pretty excited to kind of go through this material and see how it links up to what you all are doing. So at a high level goal, I'm kind of interested in creating artificial agents in the wild that can do all sorts of things. And in recent years, we've started to see some really dramatic successes. And a lot of them have been coming from Google and Google related companies, whether it's at scale robotics and labs, and then also games with DeepMind's AlphaGo work. And what we have to think about is what are some of the key processes that are enabling these successes. So at least in terms of the AlphaGo series of work and what is now expanding, there's really been pushing hard on using reinforcement learning techniques and scaling up these processes. And in academia, we really don't have the same ability to scale that they do. So what I've been studying is kind of this reinforcement learning paradigm and thinking about what we can learn from it and what it means for creating intelligence in the future. So the next step for these projects is, if we're going from successes in games, which are very well known, very closed environments, we want to try to translate these methodologies to what I would call dynamic and unstructured domains. So that's a very broad terminology, but generally it means domains where we don't know as much about the world can change over time, and also like the space of complexity can increase dramatically. And some examples will be autonomous vehicles, physical sciences, and then two of the biggest economic drivers are financial markets and logistics. And kind of what I have been following is how people are starting to apply these. So I've recently went through a long job search, and people are starting to work on a lot of these. So actually, like if you talk to people at Tesla Autopilot, they're trying to use mu0 plus transformers to generate vehicle behaviors, which is wild. And like DeepMind's been pushing a lot on machine learning for science, where when I was at DeepMind, they were working on this Pulsar project, which is trying to improve the efficiency of nuclear fusion, fusion reactions through deep reinforcement learning, primarily from sim to real. And then there's other work in AlphaFold and biological sciences. And I would guess that there are big banks or whatever trying to do this, and they're just not going to tell us that they're making a ton of money. So these things are all really happening. And I think there's a lot to learn and even more applications to work on. And kind of what my PhD has been focused on is kind of why maybe we want to use machine learning for robotics. So these are some famous examples from pretty shortly before I started my PhD, which is the DARPA Robotics Challenge. And the question is like, why do robots fail in these ways? So these were really well-engineered robots, so teams of the best roboticists in the world, and they fail in these ways that look almost innocuous. It's like, we really want robots to be able to do what they're doing here. And what was happening is these robots were designed in labs, and they had to kind of generalize to these other tasks or tasks that they knew in slightly different environments. So we really want robots to kind of be able to make this step and have these interesting behaviors in the real world where they might not have seen it before. And more specifically, kind of my background was in these robots called microrobotics. So I did my undergrad in MEMS in electrical engineering, and my advisor at Berkeley, Chris Piester, makes these robots. So like the Ionocraft and the jumping robot here are from his lab. And my task was to kind of come in and demonstrate control on these robots for the first time. And then this kind of gives a certain scope of problem, which will make more sense why I chose model-based RL. And we don't have a strong prior on the robot dynamics. And that's kind of because we may design these from first principles in physics, but in the real world, there's hand fabrication. So we don't really know the dynamics and it can change at each test. And then these robots are assembled by hand by grad students. So the cost is extremely high. So if you break one, you have to spend hours making a new robot, and that happens a lot. So essentially the method that we want to use to generate a controller wants to mirror these challenges with the strengths of the controller. So managing changing and challenging dynamics, we want a model that can kind of capture a lot of different ways that robots can move in the world. So something beyond just linear dynamics, and then be extremely sample efficient so that we don't have to make as many robots to get this to work. So a fun video to get things going is I showed up at Berkeley and I was shown this video, which is an open loop flight for a robot called Ionocraft, which uses about 2,000 volts to generate an ion wind. So it's a literal quad ion thruster, and we were trying to do controlled flight on it. And we really needed the most data efficient method that we can, and to just try to show that we can control this for one trial. And this is a bit of a segue, but it's kind of like, why would we even look at something where we learn a model? And generally, there's a lot of literature that shows that humans and other intelligent creatures will use models as an internal representation of the world. And this can be used in many different ways for decision making. And if you kind of take this biological motivation and look at what was happening in the RL community, where pretty much every model-based RL paper at the time is just saying like, okay, you get a lot more sample efficiency from doing model-based RL. There are other downsides that people aren't talking about as much at the time, but we kind of converged on this idea of trying to use model-based reinforcement learning, which generally is a pretty broad framework. And what it means is that while an agent's performance is improving, the agent will act in an environment, and this will get data in the form of an MDP. And then with this data, the state's actions, rewards, it'll learn a model of the dynamics. Here you can see an example, which is maximizing the log likelihood of transitions, where the dynamics model models a distribution of next states from a current state and a current action. And then with said model, there's some optimization function that the agent uses. Here is shown just like an open loop finite time horizon planning problem with the learned model. And there's a lot of new literature where model-based RL is kind of becoming blurrier, where these optimizers can take a lot of different forms. But this one is pretty simple to start with, which is just it's really similar to MPC. And that's kind of where I will start to go deeper into model-based RL. So I'm going to talk about how you can use a learned model to generate a controller and use that to make decisions over time. So this is kind of where we're going. I'm going to go a little bit deeper on what an example algorithm is in model-based RL. And then I'm going to talk about how exploration may or may not work in that. And there's a lot of open questions, and talk about some of my recent work from my internship at DeepMind, which is related to model-based RL, offline RL, and kind of exploration all in one, which is really exciting. So if we have a dynamics model of the world, here's a different parameterization of the prediction. This is called delta state, which is just because the model is actually modeling the change from the current state to the next state here, rather than just modeling where the next state will be. That's mostly a numerical detail, but what happens is we want to predict trajectories so that we can take actions that maximize long-term reward. So in order to predict trajectories in the future, we need to kind of pass this model in upon itself. So for each forward pass, we'll kind of move from left to right across time steps. We'll do this again. You get this composed network passes, which is kind of like a recursive function call on the dynamics model. And this gives us some interesting properties in what actually happens with the trajectories, but really it ends up being a balance between accuracy and horizon. So if you go further into the future, the accuracy tends to degrade, which is pretty challenging because often the prediction horizon is a set hyperparameter, and it's not well addressed in the literature with what that should be. So if we can predict trajectories here by this recursive function call, the next question is like, how do we actually use that for model-based RL? So kind of how I'll refer to this in the talk is we're unrolling trajectories with respect to some policy pi. And here the policy pi is a proposal. So it's giving you a distribution of actions from a current state. So here you can see at time step 0, that's the initial state. And this distribution of trajectories is a whole bunch of different action sequences by some proposal. The proposal can be purely a random distribution. It could also be learned in like a model-free RL setting. So what we do to use a unrolled set of trajectories is that we do something simple that's called like sample-based model predictive control. It's the simplest thing we can do, and a lot of papers do different variations on this. So once we have a model, we then give this model with the proposed action sequences to some optimizer. The optimizer here is a discounted reward over the horizon. And what it does is it really just selects the sequence of actions that return the highest reward. And what you then do is you then pass this reward back into the model, or you pass the agent back into the, you pass the action back into the agent takes an action. And what you can see is that the actual world dynamics will evolve slightly different than what the predicted dynamics were under that action sequence. So it's really like you throw a bunch of actions at the model, it predicts trajectories, you select the predicted trajectory with the highest reward, and you go back. And you kind of repeat this process over time. And every so often you retrain your dynamics model. And this is how a model-based RL training loop will come about. And where I first did this is we used a crazy fly quad rotor where we kind of just started from random, let it crash itself a whole bunch of times. And then eventually the model got good enough where it could do low-level control just for stability. So this just had an IMU on board. So we weren't trying to do position control. We were just trying to get it to hover and not crash, which is mirroring the ionocraft that we talked about before. So with less than 10,000 points of training data, this was able to hover okay. It was not amazing performance, but it hovered in an okay manner. It would drift a lot and crash into the wall or crash into the ceilings. But we really showed that you could kind of demonstrate a basic controller without a lot of data. So 10,000 data points is at like 50 Hertz is a minute or two of data. So it's really not a lot of flight time that you need to train a okay model. But this framework, while it's simple, it definitely comes with kind of some challenges, and these are where a lot of my future work went. So when we go back to this prediction formulation from the beginning, where I'm kind of recursing over the dynamics model, that compounding error over long horizons is not well characterized and known to kind of make it hard to select good actions. And then there's a second issue, which is what we call an objective mismatch between model accuracy and action choice, which is we have two separate optimizations. We're optimizing a model to be accurate, and then we're optimizing a controller to be high performance. And those two optimizations are not well correlated, or they're not connected with derivatives or something else that we'd want to do with machine learning. So that's kind of like a future direction, is like, how do we actually make this sample-based MPC better performance? Because we don't just want an accurate model, we want to solve the task at hand. Anyway, so that's kind of my discussion on what, like, that's just generally an example for how you could do model-based RL. I don't know exactly the audience's background here. So if you have any questions on that, I'm happy to go through it again, because the talk from here will kind of build on that sample-based model predictive control framework.
Nathan, that second point that you made about the objective mismatch is, I remember reading that paper when you wrote it, and it was really cool. Have you had any kind of insights on exactly how the fact that we're optimizing the model to be accurate, to maximize the likelihood of observed transitions rather than to maximize the performance of the policy optimized through the model? You know, how exactly does this affect the model? Do we have kind of, I mean, I don't know, this is a vague question, but do we have something more interesting to say than just that, of course, it's not optimized for the correct objective? Do we know kind of any systematic biases this introduces, for example?
Kind of. I'll go present a couple more slides on this and talk about my intuition. Okay, I wasn't sure if I was going to go into detail on it, but I have them, and I'm going to do it because I think they're interesting. So I'm going to essentially breeze through talking about it. And the specific word bias is something that's interesting to me because I want to learn what those are, but it's really hard essentially because of gradient descent, which is so much averaging. So it's like hard to see specifics when we're averaging over everything. So to kind of talk about objective mismatch, what the origins of model learning for control is that like system identification was trying to use these things called elicitation trajectories. So this kind of flower shape is supposed to illustrate elicitation trajectories, which are hand designed trajectories of an agent in a state space to cover the area that you want to be able to model accurately. So they wanted to learn a global model and then learn control. And reinforcement learning kind of operates in this different way where you repeat a task. So you observe a task specific data set, and then you kind of iteratively learn a model and control over time. And the model's performance determines what states you get to. So you kind of get this focused envelope where the data is really centered around the task, and then it kind of falls off nearby. And the distribution can take different shapes depending on what you're doing. But there's a big difference between what we were motivated by, which is we want a general model to solve a bunch of tasks, or like we wanted one model per one domain. But in reality, we're getting a task specific model, which is really a subset of the domain that we're studying. And then what will actually happen is pretty interesting. So I'm going to just jump ahead to one experiment, which what we did is in this paper that Dinesh brought up was that we did an adversarial attack on the dynamics model performance, which is like if we take a dynamics model from a model-based RL agent, and then what we want to do is we want to fine tune it so that the accuracy can go higher and the performance will go down. And what we did is we took like a gradient free optimizer CMAES to optimize the weights and biases of the output layer. And then we just let it fine tune the model on cartpole to maintain this log likelihood. So log likelihood is a measure of the accuracy. And it wasn't so hard to just get this basic optimizer to reduce the performance while keeping the accuracy the same. So it's kind of doing a search space over the models of similar accuracy while trying to find a model with the same accuracy with lower performance. And this experiment is kind of key to my intuitions about this now, which is that there's a few things. So like starting with okay, I'll go through these points and then kind of say my summary. So it's like, my intuition is that we lose model accuracy on areas important to control. And what that means is that if you have like a control sequence of 20 to 50 steps, I think a lot of times there's like a couple actions that are very important to that decision-making, to that trajectory. And what happens is that like, if we do gradient descent, we're often taking batches. So we take a batch of like 32 transitions and pass that into the dynamics model. And then what happens is we take the average error from that batch, and that's our gradient step. So if only like one of those points is actually important for the model to be accurate on, it's getting totally averaged over everything. And then we're kind of it's hard to make the model prioritize that one action. And kind of what this means in like the gradient descent space is that there's the subset of models that are accurate and high performance is much less than just accurate models. So it's easier to find an accurate model than it is to find an accurate model that actually solves the task. And this is really hard to measure. So it's like, this is purely intuitive speaking. I don't have an easy way to actually demonstrate that. And kind of later in the talk, I have another couple of ways that I see this coming about and like another related work that I got to work on. But I think it really goes down to that low level of like what data we're feeding into our gradient descent.
Yeah, that makes sense. And it's kind of quite intuitive, right? So one way to kind of quantify this would be, for example, if you took expert data. I mean, I know this is a bit of a tangent from what you were planning to talk about, but maybe if you can, let's take like a minute. But one way to kind of quantify this would be if you took an expert and on the expert trajectories, you notice that the accuracies of these models that were equivalent on the entire state space or on all the data that you've gathered so far, the accuracies are very different on the expert state action pairs. And you find then that those accuracies on the expert kind of manifold of states, those accuracies are more predictive of actual kind of planning success performance, right?
Yeah. So, okay. So we like kind of did this. I don't have the slides with the results for it, but that's what we did in the paper. And you like get better data efficiency by reweighting. If you reweight the transitions close to the expert, you get better data efficiency with model-based RL. The problem is that you need to know the expert trajectory ahead of time. So it's kind of like merging RL with imitation learning, but it was like pretty easy to set up. And if you do know the expert, you could get a model that is much higher performance with much less data. it's kind of like a firsthand confirmation of what we did, but I think there's a ton more to work on in that space. It's very interesting.
Makes sense. Yeah, thanks.
Yeah, we'll kind of revisit this in a couple different ways through the talk. It's a lot of how I view. It's like trying to learn what dynamics models are actually doing, and it segues nicely into what we're talking about next. So like I'm going to talk about exploration in model-based RL, and I'm really going to try to link together ideas from like intrinsic curiosity and model-based RL.
I think there's Oleg has a question.
Can you actually hear me? Do I need to be closer?
No.
The mic. All right, I don't think you can hear me.
I can hear you. I can hear you.
Okay. Yeah, I just wanted to ask about the other slide that you've shown, the 2 slides before. Just a small question. The one with the model icon. Can you actually hear me? Are you sure with that?
This?
Okay, yeah, that's fine.
Yeah.
This seems really interesting. I'm wondering, I guess, 2 questions. Why do you think it's possible in the first place to get a better accuracy than the start? So like how was the start optimized and why is it not the best accuracy?
Okay.
Like, is it like a model capacity issue where it's somehow not as good, like, or did you optimize it with a different optimizer that's not as good as
I think it's like this is a very sampling problem. So we like selected a model from one trial, like we ran pets on the existing code base, and we just like took a model from what we did is we took a model from like a high performance pets run, which is the algorithm. So we took one model, and then what we do is we like run that model 5 times in the environment to get the reward, because sample-based MPC is really stochastic. So sometimes you just get trials that suck, just like randomly by initial condition in combination with sample-based control. And then we like fine-tuned with respect that one model with respect to the output layers. And like each time we selected new weights, which was like weights and biases of the output layer, then we ran that 5 more times. So it's like kind of slow, but it's definitely highly stochastic. So it's like there's definitely some sampling here. So these like this 2D plot does not have error bars on it, which definitely is somewhat like I fully admit that. Like this is not with, it would look a little bit different if you had error bars, which would also be interesting, which is kind of why I lean on the intuition of this more than saying like these specific numbers are the ground truth here.
I see. I am still pretty confused about that actually, but okay. But then I guess another question to put it in a different way. What would happen if you ran your new optimizer and you just maximized the likelihood? Do you think that would find a better likelihood than the start?
Yeah. Sorry. Also to answer one part of your questions is that this is like on a constant validation set.
Okay.
This is also years ago, so I think that the CMAES optimizer is getting the measure from a validation set. Like it doesn't have access to it, but you're running this and it's getting returns of this number. Like this is your test set accuracy. That's what I think. I'm not 100% sure on what that data set was, given that it's like 3 years ago.
Okay. I guess I'll just check the paper. Thank you.
Yeah, I'm happy to discuss. I think this is fun. Okay. I also think that it's fun that you're here because the next stuff you'll potentially give good questions for what I'm doing. Okay, so now I'm talking about like kind of the links between model-based RL and intrinsic curiosity. So there's been a lot of advancements in people using essentially curiosity models for exploration. So intrinsic exploration is the idea of imbuing your agent with an internal reward function. And then curiosity-based exploration is the idea of using some internal model and looking at the error of that model as the internal reward function. So it's learning some model, which often takes the form of a dynamics model, and then optimizing an agent to look for certain conditions in the dynamics model that might be interesting states. So there's a lot of recent work, and I see that I didn't change the external examples, which is this from when I did work at DeepMind. But essentially, there's a lot of work on using these dynamics models as a source of motivation for agents. And what they do is you train a dynamics model, and then you kind of optimize either the variance of the predictions or the error of the predictions. And how this often works is through storing this transitions in a replay buffer, and then you like train a model-free agent to optimize the intrinsic rewards in the replay buffer And then that policy is your exploration policy. And kind of what we wanted to do in this work is to use online planning to kind of look over the current the current version of the curiosity model, and then use that to kind of navigate to interesting states. So there's kind of there's a nuanced difference here between like off policy RL and then online planning. And the talk is not to compare, the point of the talk is not to compare them, but we want to have an agent that can look ahead and look at the current version of the curiosity model in order to kind of see what is currently interesting rather than revisiting a state in the replay buffer that was interesting at the time of training. And there's recent work, like I'll talk about Plan to Explore, which is another work that kind of uses a planning approach to do exploration. And it's really linked to model-based RL, and then kind of talk about this whole space and where we could kind of link up some ideas. So, yeah.
Can I ask a high-level question about something you just said a little earlier? So for this intrinsic curiosity objective, you made it sound like people either choose error or variance, and I'm curious if there's some trend that people have discovered that on like the trade-offs between those choices.
I would honestly really like to know, but they're very similar, which is interesting. So, like disagreement is the idea of using an ensemble of models, and then you look at the variance of the predictions through the ensemble. And then most of the other ones use direct error. So like intrinsic curiosity model is based on the error of a dynamics model in a latent space confined by an inverse model. So this is like a forward model. And then random network distillation is a forward model where instead of learning a dynamics model to the next state, it just learns a latent state that it's trying to mirror to. And they're all very similar. And what I'll show you is that they actually have pretty similar performance, which is kind of interesting. There's some deep questions about what they're actually doing that I don't address, but I don't think there's actually a clear winner. I think it's kind of like by application that certain people find certain ones to be better.
Sure, thanks.
Okay, so I'm going to revisit this sample-based MPC that I talked about and talk about kind of my intuitions for how exploration happens. And this stuff is all not well documented, and I would love to actually empirically study these mechanisms. But kind of you want to start with like what causes exploration when you're sampling a bunch of action trajectories and then looking into the future and choosing the one with the highest reward. So what's happening is these predicted states are interacting with the environment reward function or a learned reward function to mirror it. So it's like if you predict an incorrect state, it could be viewed as having high reward. And is that like, does that happen in a structured way or is it purely random? And I'll go through some examples. And like, there's no explicit exploration reward in the sample-based MPC framework that I showed earlier. There's no value function. There's no like epsilon factor for taking purely random actions sometimes. And it's kind of strange, but it's just like over time, these actions are selected based on the model accuracy. So if your model is inaccurate or accurate, you're going to get different distributions. And then it happens to work. Model-based RL kind of works, but there's no explicit exploration mechanism in a lot of the algorithms that I've worked with. And then what it's often attributed to is exploitation. So it's like certain actions exploit the model, and then the optimizer selects them, and it sends it to a new area of the state space, and then the model learns that new area. And I think it's very interesting. So let's kind of talk about like different scenarios where this would come up. So there's kind of two areas in training that I'm interested in. There's a high accuracy model, which is late in training on a specific task, and a low accuracy model, which is early in learning. At the first trials, you are taking purely random actions, and often algorithms do that. But like, what is the difference between these and what will happen in exploration? So what I think with the high accuracy model is that most of your action candidates are going to be relatively modeled, relatively accurate. And it's like every so often you're going to get an action candidate that's close to what you wanted to do, but slightly different, and it'll take that. And I think the action distribution will kind of shrink over time. And this would be much more of an exploitative exploration mechanism for whatever that means. It's like, I think that it's a narrower distribution, but there still is some level of exploitation that you can never get rid of when you're doing sample-based control. It's really hard to get exactly optimal control with this. But with a low accuracy model, it seems like it's going to be a lot more random. So if you have a model, like if you initialize a neural network and don't do any gradient steps, that's effectively going to be random in terms of the action selection. But when you take a few gradient descent steps, what is the, like, I want to know what the structural bias is constraining the action selections. Like, so which action selection is going to return a trajectory that seems like high reward, because then that's what the agent is going to take. So these are things that I don't know and I've been thinking about for a long time, and I would love to learn about them. And it's like, if we can kind of continue, we can look at how this fits into the framework we're using. So like, how do we actually characterize this? So that's why I'm interested in intrinsic curiosity, where they use dynamics models for exploration, but the agent is maximizing the dynamics model error rather than kind of maximizing the environment error. And then there's the plan to explore work, which uses kind of background planning, where it takes states that it visited before and it unrolls them. It imagines the transitions, and then it kind of uses that with an intrinsic reward. And what we wanted to do is kind of use online planning to kind of see what the difference would be between maybe plan to explore, which is this background planning, versus using online planning and then kind of selecting these high reward states. So how do we kind of, if we go back to this framework, how do we modify this to, so this is the dynamics model. And then how do we modify this to have some reward function that encourages exploration rather than just using the environment reward? So this reward function here is kind of the environment reward. In half cheetah, it's maximized forward velocity. And what we want to do is kind of modify this to actually use intrinsic reward. So what we did in this kind of intrinsic model predictive control, which is buried in this paper that we wrote, which is about offline RL and exploration, was we add a curiosity model to this sample-based exploration. And the one that we found to be most successful was random network distillation. And on average, but on some environments, the dynamics dissimilarity or disagreement was really good as well. So it's like, there's not one best curiosity model. So what we did is now we're training two dynamics models effectively, which is definitely not the most efficient thing, but we can kind of separate the effects. We had one dynamics model for propagating trajectories, and then the other model was purely to evaluate the reward for exploration for the agent. And kind of the goals that we wanted to do is we really wanted to reach novel states in that instance with online look ahead. So we would have the current instance of the curiosity model, of the R&D model, and we would pass in states from this predicted trajectory. The predicted trajectory is a sequence of states and actions. So we can evaluate this with this R&D model, and then we can kind of execute it in the real world. And this kind of online planning approach really performed really similarly to a lot of existing work, which is kind of interesting. And I can kind of talk about where did I put this? Okay, I have a slide. My slide was being weird, but what we did is we kind of evaluated this with a suite of exploration agents, and a lot of them performed similarly. So this is kind of transitioning into the evaluation metric that we used for this intrinsic model predictive control, which is something that we called explore to offline.
Sorry, Nathan, I have a question.
Yeah.
Could you just clarify again, what do you mean by online planning versus background planning that you talked about?
Yeah, so online planning is definitely what I mean by model predictive control, which is your agent is at a state in an environment, it plans trajectories from that state, and then it selects the best action sequence. Mm-hmm. And background planning is totally separate from the agent runtime environment, which is kind of like a training mechanism where in a replay buffer, you have a bunch of states that your agent actually experienced. And you can use a dynamics model to simulate transitions from that state that you already visited, and then kind of use that to update a value function or understand what the dynamics model is doing. And the key difference is that online planning is from a new measured state, and then I say background planning for states that are in the replay buffer.
Got it. Yeah, another question. What's the connection between intrinsic model predictive control with classical methods that use optimism as a reward bonus for exploration? Because you can think of the reward bonus as like a intrinsic curiosity reward from let's say R&D, that kind of thing.
Yeah, I'm not an expert in the optimism literature. I would kind of expect them to be similar based on what I've seen in kind of evaluating a bunch of these agents, but I don't know exactly. I think it's really interesting to kind of see what the behavior differences are when you use different mechanisms, because intrinsic rewards are kind of different ways for encouraging intelligent search, really. It's trying to search the state space, and I don't know exactly the subtle differences between how those will operate.
R&D is kind of like a way to implement optimism in the setting where you can't just keep account of every state, right? R&D is kind of like a way to implement that.
Yeah, I guess I don't know what the word optimism exactly refers to, and if it refers to a specific literature item or if it's kind of an idea.
Yeah, basically, if your model is more uncertain for the dynamics of state action, you have higher bonus, right? So it's kind of like a deep RL implementation would be like ensemble disagreement or something like that.
Oh, okay. Yeah, so these are closely related. So with intrinsic model predictive control, we evaluated it with like R&D, which is optimism over like if your dynamics model has seen the state before, and then also disagreement. And the average performance is pretty similar. It's kind of like on a domain by domain basis that the performance differs. And we tried to look at what is happening and try to understand why one is better and one is not, but it's pretty opaque because you just see that they have slightly different state action distributions, which results in slightly different performance on each domain. I'm happy to talk about that more later, and I could send more slides to kind of motivate that. I don't have all of them here right now.
Nathan, can you quickly comment on why we should use online planning versus background planning in this like exploration? Because you just mentioned that the results seem similar, like between the two. So why should I use one over the other?
Yeah, my motivation for online planning is kind of to mitigate the delay in exploration signal in the data set. So there's a classic problem in RL where the RL agent has to jump off a cliff in order to see that there's massively negative reward. And if you learn a dynamics model, my goal is that you can generalize just enough to not actually have to jump off the cliff. And you would do that by kind of looking ahead at like decision time or online planning. That's my motivation. And I understand that is entirely biased, but I think there's just like a little bit more, you're adding more compute at the decision time to hopefully eliminate some negative consequences and get a little bit higher performance.
Well, thanks.
Okay, so I'm now going to go and talk about what the motivation for this intrinsic MPC work was, which is what we called explore to offline. So if you can kind of take a step back and view RL as two separate processes, which is that one process is you have to collect the best data, which is where exploration comes in, which is what we've talked about a lot. And then another question is inference, which is like, how do you get the best learning method for a specific task in a specific domain? And this inference method, when separate from collection, is offline RL, which is really exploding in popularity these days, which is you have a data set, you want to get a policy. And kind of this collect and infer framework is a way to study both of these mechanisms individually. So what we wanted to understand was, what is the best collection mechanism? Like how do you get the best data from a domain to then learn a set of policies? And what this will look like is you kind of have an agent and you can decide on a couple different ways of collecting data. If you just look at the data you're collecting during a task, it kind of mirrors this drawing I showed earlier, which is you have really task-centric data. You store that in your agent experience, or you can kind of do this task-agnostic exploration, which is another way of describing intrinsic exploration. And what happens if you train a bunch of policies? You take a few different tasks, you train policies on each of them. The idea is that online learning won't generalize across tasks, but this kind of task-agnostic exploration has the potential to generalize across all the tasks in the domain by just automatically collecting the data that you want. And how we evaluated this is that we implemented a library of exploration agents, and we collected a bunch of data sets in this task-agnostic fashion and wanted to find, and a key point was trying to do sample efficiency. So we looked at like the lifetime of these agents. So all the transitions that they collected while exploring, and then after you collect data, you can choose a task and label your data for that task-specific reward function. And with offline RL, you can then get a policy specific to your task, even though the data that you collected was general in its nature. And this is what we call explore to offline. And interestingly, there was some other work this is from when I was at DeepMind, and there was other work from Peter Bill's group at Berkeley that has almost the same thing and very similar results. And we released it in like the same week. So if you're interested in this idea, there's a lot of people starting to work on it, which is very exciting. And kind of in summary, the results that we had were that across these task agnostic agents, so we implemented like 7 task agnostic agents, and I didn't list all of them here, but in the lower dimensional tasks, so you can see we evaluated these control suite tasks, which are like ball and cup, finger, reacher, walker, which are a series of like locomotion or manipulation tasks. And on the low dimensional tasks, this task agnostic data collection into offline RL was really able to mirror the performance of if you just did task aware learning and then applied that data into offline RL. So here the best result, like the best quote unquote results we got were with this new intrinsic model predictive control agent that we implemented, but they were all just using vanilla R&D or vanilla disagreement or model predictive control with disagreement. Pretty much all of these exploration agents were really within error bars of each other. So they're all performing really, really similarly, and getting more performance is relatively hard. So it's like we did implement something new that was quote unquote better, but by such a slim margin, it's really asking questions of like, what is actually the driving mechanism behind exploration, and like what are the models that we're learning doing. So I'm kind of going to start heading towards wrapping up and thinking about that specific question, which is like, what are these models that we're doing, models that we're training doing, and how can we actually use them? So it's like, I really see traditional model-based RL and intrinsic curiosity being very similar. They're both training dynamics models, but they're using them in different ways to optimize the agent. And traditional model-based RL is task-focused, while intrinsic curiosity is task-agnostic. And really these training loops look really similar. And it's the question of like, what are the dynamics models learning? Like, what are the areas of the state space where one is accurate and one is not? And why are these actions being chosen by each of them? And I think these are really interesting questions. So they kind of both share these properties where they're doing self-supervised collection, self-supervised updates of the model. There's really a lot of interesting literature that's shared between them, between planning, and then model-free RL is coming in to generate value functions. And it's like, I think it's a pretty deep question of like, why do these work or why do these not? And like, can we combine them in interesting ways? So like the intrinsic model predictive control that I showed that we evaluated in terms of offline RL, it'd be really easy to implement that as an online RL algorithm and benchmark it against existing things, which is like what happens if you add an exploration bonus to a model-based RL algorithm that was exploring by exploitation. Does it make it better? Does it make it so that it no longer works? Like, is that exploitation mechanism really important to model-based RL? And I don't really know. It's a hard problem, but I think it'd be really interesting to study these links. And I'll kind of talk about some other things that I'm going to be working on kind of as a transition. And a big thing that like I think is kind of limiting all of these fields is that we use these one-step models for transitions. So all the times I talked about a dynamics model is that it predicts a next state from a state action pair. And there's a lot of developments in kind of just deep learning generally about learning different representations of dynamics or using different prediction mechanisms. So here on the right is like neural ODEs, neural differential equations. And for these physical domains, I think we have a lot to gain by using these basic inductive biases that we know about the world. So like we know that dynamics follow like a double integrator formulation, or there's rigid body dynamics. It's like, can we use these and just get these basic inductive biases into the model-based RL algorithms we're using in the real world and see if kind of accuracy goes up, if objective mismatch goes down? It's like, it just seems like kind of low-hanging fruit, and using models that are a bit more intuitive. And one-step models are good because they're easy to implement, but they're not going to be the best at any one thing. So if we get a bit more specific models, we might be able to really push the limits on specific applications and then kind of keep making progress on understanding how these models work. And kind of, a lot of my work is questioning like, why does model-based RL do this? And what I'm starting to become interested in is like kind of the intersection of model-based RL agents in the real world. So if we go back to these artificial agents that we talked about, it's like, there's little understanding of why like why model-based RL agents actually continue to evolve over time. And I'm interested in kind of, if we put these into the real world, what's going to happen? So there's a couple different ways to think about this. The one on the bottom is probably closer to a lot of roboticists' framing, which is like decision time understanding, is like, if there's one really important action, why does that go wrong in a way that causes the robot to go into an unsafe region? It's just like, what is special about that one action and what causes the failure? And then if you zoom out, there's kind of this behavioral estimation, which is, if you know that you're implementing an agent to get a specific set of long-term behavior, it's like, for a game, it's really simple. You're implementing an agent to get grandmaster performance on a game. But if you have a self-driving car or a delivery robot, it's like the space of behaviors it can take on is so broad. It's like, what is limiting what in the data is causing the learning procedure to take a specific path? So like RL seems to be very path dependent, which is like, it's developing its own curriculum. And we don't really know when RL is going to fail. So like, there's a big difference between RL failing in a simulated task versus a real world task. And I'd be really interested in understanding, like, it's kind of like understanding towards making robust learning curves. We like can't afford big drops in performance if we're using these in the real world. And I think that's a really interesting question linked with this framing of kind of understanding what model-based RL is doing. So before I wrap up, I wanted to thank collaborators. This is all the people, or most of the people that I've worked with on this stuff and other stuff in my PhD. And it's really fun to be able to work with such a kind of broad and diverse audience. And then to wrap up, it's like, what can we understand about the links between exploration and sample-based model predictive control, and then some of this work in curiosity-based exploration that I was talking about. And I'm going to be starting work in industry research. So if you want to discuss these things, I definitely have time to do so and would love to discuss this further, and have enjoyed this conversation / talk with you all today. Thank you.
Nathan, maybe I'll go first. I remember, yeah, in your like paper on the one-step error of the models, like I remember like just reading some follow-up papers that say that models that overfit to the current data set are basically bad for exploration, because basically they become very accurate on the current data set that the policy has collected, but because they're so overfit to that, if you try to do planning with them and things like that, they only predict they basically only predict the trajectories that they've seen so far. And I was wondering if it makes sense to have a model objective that that explicitly encourages exploration. So something like I think I've seen some papers where they've just kept bad models from the ensemble. So like in pets, instead of keeping like the top 15%, they also keep like the median models, and they show that that improves performance specifically by adding some, I guess, like blurriness in the dynamics when they do planning for exploration. Do you have any thoughts on this?
Yeah, I kind of like this. It's also like, the dream of what I want to get to is dynamics models that are kind of cross-domain. And it's like, you can't have if you want to do cross-domain anything, you really need to have a broader representation. And it makes sense to me. It's like the developments in deep RL are so driven by like getting the number to go really high and be really like just getting the learning curve higher, that it's like making sacrifices at these other things like exploration by kind of eliminating these kind of fuzzier models. So I do like that. And I think in like real world applications, that could be very useful. I don't know. I'll definitely think about that more.
Nathan, on the thing that you showed with kind of your last paper that you showed, where you were talking about comparing completely intrinsic motivation generated data plus offline RL, and comparing that with online approaches. Did you also kind of like compare them with equal amounts of exploration data? I assume not, right? I assume that for the purely task agnostic exploration, you actually need much more experience in the environment before you're able to learn good policies for a variety of tasks. Is that right? Or?
Are you comparing the data set for exploration versus like online RL, or which?
Yeah.
Okay, so I pulled up the paper.
Specific online RL. Yeah.
Let me pull up the paper so I can kind of show you. So it's just, I didn't include all of these in my slides, but essentially what we did is we made data sets of fixed transition size, and you can see like left is the collection reward, which is like the environment reward during collection, and the online agent, which is MPO in this case, task aware, means like online RL. In this case, it starts collecting reward a lot faster, and that does translate. And the right side is what the offline RL performance was for a fixed data set size. So you can see like it's thousands to millions of transitions, and it definitely does perform better with less data, but there's a clear trend of adding more data with task agnostic learning where that does improve the performance. And it's not like at collection time, it's kind of a 0 to 1 difference, but when you're actually training with offline RL, the data set sizes are starting, it's like an order of magnitude, but it's not a ridiculous amount difference. This is a lot more information, so if it's just totally overwhelming, I don't need to show this.
And what was the one task on which the trends were not observed? I forget now. I think on the table that you showed, it was for like 3 out of 4 tasks. It was
so is the Walker task, which is like a much higher dimensional and much harder problem. Yeah. It's less inherently stable. So when you start the Walker task, it just falls on the ground, and then you have like a 10 plus dimension action space where it just kind of like scrambles around. But in order to solve the task, it needs to be able to like stand itself up, which is a really like a stability problem as well. So there's a huge, so essentially it's down at the bottom here as well, which is like ball and cup is easy, finger is easy. It's just like a couple dimension manipulator. Reacher is a higher dimension manipulator. And then Walker is like essentially like half cheetah squared. It's just like a much harder than cheetah locomotion problem. So there wasn't really as intermediate. There's like easy, medium, and then very hard, where it would be nice to see on some tasks that are kind of in between that.
Mm-hmm.
Could you give some like qualitative comparisons between the task agnostic agents, like maybe in the Walker case?
Yeah. I wish I don't have access to the videos because Google locks everything out, but this is pretty interesting actually. So generally there's a big difference between the online planning and the kind of other task agnostic agents, which is the online planning, if you give it a static environment, like curiosity reward. So R&D like is a reward function over the state action space. What would happen with the planning algorithm is that it would just stick to an interesting state action space. So it would just like get the agent, it would like flip the agent over and then kind of balance there and just stay at this state action space that's high intrinsic reward. So it's really clear that the planning is like trying to get exactly to the R&D model, which is like almost exploiting the R&D model. So we did add a tiny bit of randomness in, so it didn't just exploit it, which was kind of funny. You had to like add exploration on top of our exploration. Whereas some of these other, like if you compare that to pure random looks really, really jittery all the time. And then the kind of the other curiosity models with a model-free RL algorithm do things that are in between, where some of them are kind of like closer to random and then do some interesting things like flip over. And then intrinsic curiosity model we found was like liked to find these really weird behaviors and just stick to them. So it like really liked to cartwheel the half cheetah or whatever. But even if we like see these different behaviors in the videos, this is over like 10 million transitions. So we're sampling the videos. So it's definitely adding user bias to it. But it tends to, like for me and the other interns that were working on this project, we all agreed that there were like conceptual differences when you look at them for a long time, but not in ways that are like numerically dramatic. So it doesn't show up in the data that much, but there definitely are kind of these flavors of the different algorithms.
I think it's really interesting that it stays in place for a long time. Like the
I know.
MPC.
I reached out to try to get a video for this talk. It's really, really interesting to see as someone who does planning, because it's like doing a minimum cost problem on this like numerically defined state action space, where it's just like a neural network is defining the state action space and it just like finds the configuration that it likes.
You would think that with a long enough planning horizon, it should do some other things aside from just staying in that state, right? Unless you're saying, I guess, staying in that state is the best R&D reward. So it should actually.
I think that's what it was doing.
I see.
Or it's really hard to get it to another one. Like the configurations were never the same. So it really was that every time the R&D was different, it would get itself in a different position. And it wouldn't always get into a unique position. But it was like across the domains, it was very normal to kind of see it just freeze. So it kind of looks like the video breaks, but it's really just that the agent is super stable around this really weird position.
So Nathan, coming back to that question that we discussed briefly in the middle, the tangent that we went off on for the objective mismatch stuff, right? So my intuition there is that it's obviously important to focus on the set of states that is actually observed in a good trajectory for the task you're looking to solve. But even among those states, actually errors on some states within an expert trajectory are worse than on other states. Right? So there are some states that are more critical than others. So for example, let's say that you're flying one of your little quad rotors, right? Making errors when you're very close to a wall, for example, are much worse than making errors when you're flying in free space, as an example, right? So that should show up if you made a plot of, kind of how you visualize very nicely the accuracies versus the rewards, and showed that there was basically no systematic trend. You could, for the same accuracy, get much lower reward if you wanted. There must be also some leeway when you restrict them all to have similar accuracy on the expert data. There must still be significant variation between the rewards of MPC optimized through those models. Is that also what you observed? Have you performed experiments like that?
I haven't actually thought about it from that perspective, but I find it really interesting. So it's like, you can almost prioritize states if like the variation of trajectories from that state has really high changes in rewards or dynamics. Like that's a way of indicating that it's an important state. It's like the state where you decide between two modalities type of thing. I think that's an interesting way to try to quantify. And openly, that type of thing is why I'm less motivated. Like I'm more motivated by something like R&D than disagreement right now, because I've worked with dynamics models for so long that like optimizing the dynamics model error or like the variance of it, it's like hard to disambiguate between what is a data problem and what is an environment problem. And you do want to prioritize this. Like, I don't know if you want to prioritize the states in the environment that are high error, because it might just be that there's one stochastic state that's always going to have high error, even if it's not important. And that's something that I think we do need to kind of build methods to look at, which links to what you were saying.
Nathan, I have a question. So in your future work, you mentioned that you want to investigate beyond one-step models for control. And I noticed that in your, for example, IMPC work or a lot of other current work, they use one-step planning during their exploration. They select the best action given to optimize some objective, right? And I was wondering, do you have any thoughts on considering something beyond one-step planning? Perhaps given my current state, I would generate a sequence of action or a plan instead of just having one action.
I don't know. I also had a slightly hard time hearing that. So I don't know if you want to repeat it in a different phrasing. But generally my idea for beyond one-step models is like learn models that are more specific to what you're doing. Like one step I think will always be like the best on average across a lot of tasks and is a good starting point because it's easy to implement. And it's like maybe for an exploration model, you're looking like someone had brought this up earlier. It's like, what if you train a dynamics model that somehow encourages exploration or is like a fuzzy model or something like that? That's kind of what I mean by that is like, let's get more specific models based on what we want to do.
Thanks.
Okay, I think we're actually a few minutes past when we usually end. So unless there are other questions, thanks again, Nathan, for taking the time to be with us virtually today. It would have been great to also have you here in person, but perhaps some other time. Yeah, I really enjoyed the talk. I think it was very informative and educational, and I look forward to seeing how this trajectory of work develops in the future as well.
Yeah, thanks a lot for having me. I definitely tried to make this like an idea-centric talk rather than just throwing numbers at everyone. So hopefully that gets people thinking about things.
Yeah, thanks again. Yeah.